All right, thank you. It's great to be here. I would like to thank SLC for inviting me to give an update on the Earth 2 mission. It's great to visit such a beautiful place, and this is the sunset. I took a picture last night. Also, this is really once a life opportunity to give a talk on the Chinese theme. I'm not sure this will be reproduced anytime in the future. So all my collaborators are listed here. So the ones in yellow are attending this conference, and Bongjing and Qiyuan are here in person. And I also would like to thank my collaboration teams, KMT-NET, and also the Earth 2 science team. So our field really has made tremendous progress last few decades. So you can see we are now discovering about 40 extrasolar planets per year, and by 2028 the number may reach about 500. And we have made progress in putting constraints on the mass function, although it's still controversial. And then this is because currently we have only about 30 planets with firm mass determinations. And you can see the red dots, the rate is not increasing as a function of year. And this will be very challenging in the near future. And this has really made some of our key science goals difficult to implement. For example, this plot shows the planet host mass ratio as a function of host mass. So the microlensing surveys are really discovering these low mass host stars, which are not accessible to other methods. But unfortunately, the mass determinations here are usually based on Bayesian analysis. And one frequent assumption is that the frequency of planets as a function of host stellar mass and distance is a constant. Dave gave a talk which question this assumption, which may depend on lens mass, but the uncertainty is still very high. Now, the second science goal we want to address is, of course, to understand the planet frequency as a function of environment, whether the planet formation efficiency is the same as in the disk or in the bulge. Other surveys can only probe nearby universe, while in our case, we can go much deeper to the galactic bulge. But without firm length distance determinations, this goal is not so easy to achieve. Now, to partially address this question, we can study luminous lenses, and we have seen a few groups doing this successfully in last decade. And this just shows one example. The PSF is around 50 milliamp seconds, and the typical lens source relative function is a few milliamp seconds per year. So if you are patient, you can wait for 10 years. You can see the lens source separated, and you can put constraints on the lens mass in this way. Now, of course, in the future, with planet detections from various surveys, including one which was witnessed first light on Friday, and the future extremely large telescope, in particular the European large facility. This shows a real picture of this facility in January 2025. And it will have wonderful laser guided facility that will have a very high spatial resolution. So this can be used to characterize the luminous lenses much more quickly than the current generation telescopes. But the question in the future is, how can we secure hundreds of hours from these very expensive facilities? If you sell each night on the market, probably you'll fetch about $500,000 to $1 million per night. So this is very expensive. And how can the microlensing community command hundreds of hours for such facilities remains a challenge to be seen. Now, perhaps to overcome this difficulty, we can go to space. And this is where the lunar mission will play a very significant role. So, well, I wrote here the first season may start in 2028. In fact, from the timeline we have seen, this may be earlier in 2027. And this will discover many hundreds of bound planets. And maybe from the very good PSF of Roman, we can detect masses or have a mass information for a large fraction of these lensing planets. And I'm very glad to see Euclid and HST will have precursor surveys in 2025. We have heard one talk yesterday, and these will put the initial constraints on the luminous lenses. Now, of course, not all lenses are luminous, and there is a different primary space we can probe dark planets, and I will touch upon two of these. One is free-floating planets, and the other one is planets around stellar remnants, in particular around white dwarfs. So here shows some examples of free-floating planet candidates. So we have currently about a dozen known. And now these have measured angular Einstein radius, and this shows two very excellent examples. Unfortunately, the rate for such a discovery of free-floating planet candidate is low, perhaps of the order of 1 per year. So in order to increase the rate, we need to go to space, as we will see shortly. Now, from such limited observations, we already see that the number of free-floating planets may be extremely common. So this shows the mass function as a function of mass in units of Earth mass. You can see this is enormous star plus brown dwarf population, and this shows the free-floating candidate population studied by Taka, and this is a bound planet population published by Wei Zhang very soon. So you can clearly see around Jupiter mass, maybe the bound planet population will be comparable to the free-floating planet, maybe even bigger, and at low mass and the frequency of free-floating planets may be much larger. So this is very important. Now, I want to come to the next dark planet candidate category. So this shows the planet mass as a function of planet hole separation for white dwarf systems. You can see there are only 4 candidates known from other methods, and there are 2 from microlensing, starting from the first one discovered by Blackman et al. So this candidate was discovered by our team. So this shows the light curve. It was discovered by Wei Zhang in June 2020. The magnification here is very high, reaching about 1500. Because this was the event he perhaps worked on during Chinese New Year in 2021, he even won a little reward for excellent paper for working in Chinese New Year. Now, this event, because it had very high magnification, so you can measure the final source size effect. And also because it has very long positive crossings. So the parallax effect can be measured from that crossing. So we can determine the host mass around 0.5 solar masses. So if it's a main sequence star, it must be luminous. And by doing a Keck observation led by Kemin Zhang and Wei Zhang, you can see the CFC image, and this is the Keck-2 image in 2023. And it turns out the blending for this event is from this faint surrounding star, not from the luminous lens itself. Because if it's luminous, then the luminosity here will be visible. So this seems to be a dark lens, and it appears to be a white dwarf. So this planet is only of 2 Earth masses. So it's the first Earth mass planet discovered around white dwarf. So this is very interesting publications in Nature Astronomy. Now, in the future, parallax cannot be measured for many microlensing events. In order to do this, for free-floating planets, we need to go to space. And this shows an artist's view of how this can be done on an L2 satellite mission. So this shows the simulation. So even for 1 Earth mass of a planet, the light curve you see from the satellite and from the ground will be significantly different. And the reason is for this sort of free-floating planet, the Einstein radius matches the separation between the L2 location and Earth. Now, Of course, we cannot compete with NASA in terms of size and money. So we have poor man's vision of a satellite mission, this Earth 2 mission. So this will be a 35 centimeter telescope, much smaller, but with somewhat large field of view, 4 square degrees. So one advantage we have is that we will co-observe with ChemT-Net from space, and it will be at L2. So I want to emphasize this is complementary to Roman, and it's supposed to be launched in October 2028. So compared to the talk I gave last year, the difference is now it's officially approved by the Chinese government. So it will go ahead in the future. So let me just recap what this mission is about. So this is a mission combining transit and microlensing in a single mission. So the transit is done by 6 28 centimeter telescopes. So this will survey very bright star transits, okay? So here you have one 35 centimeter microlensing telescope, and the science studies have been led by Wei Sheng and Hong Jing, who is here. Now, the overall science goal is to detect a factor of 10 more transit planets around bright stars, and perhaps 10 Earth-2 systems, as shown here. And in terms of microlensing, we hope to detect maybe 300 bound planets and 500 free-floating planets. 1/3 of each category will have mass determinations. So if you want to read more, you can go into this white paper. Now, in 2024, we made a lot of progress. We completed the end-to-end simulation. I think Hong Jing will discuss in the next talk. And we have started 82 items for the scientific and calibration requirements, almost completed the telescope design. And I'll mention how we are doing the CMOS detect experiments to pick the right candidate. And we also determine the data transmission process. So this shows the image level simulation. Hong Jing will discuss more in detail. So this we take into vibration and jittering, and we hope to reach a core requirement. So at 20.5, we have 5 sigma detections of signal to noise ratio 5, and at 16 magnitude, this will be 80 sigma determinations. And this shows the ideal situation, and this what we achieve satisfy our core requirement, but somewhat below the ideal situation. Now, we also select the field by doing detailed Lycos simulations and Monte Carlo simulations. So this is done by Shikai-san, who is not attending in person. So this shows the Lycos simulations. And we also select the fields, and this shows the field center that we, at which we can satisfy the core goal of 25 free-floating Earth in a 4-year mission. So the field center can shift by about 7 arcminutes, but this is this is roughly the field we will use to achieve our core science goal. Okay, so in fact, this shows the Earth 2 and ChemT-Net field, and this shows one possibilities of the Roman field. So in some fields, we will have observing data from ChemT-Net, Earth 2, and Roman. So you will see 3 distinct light curves, which will put more constraints on parallax signals. So data processing is a challenge. In particular, L2, we expect cosmic rays to be very significant. So maybe 4% of pixels will have cosmic rays in a 10-minute exposure. So this will decrease the signal-to-noise ratio by about 15%. And the difficulty is if we have short exposure, we then will have higher data rate. Of course, the cosmic rays will be reduced. And the long exposure, we have more pixels with cosmic rays. And eventually, we decided to address this issue with onboard machine learning algorithms. So this shows a similar image. So we have some machine learning algorithms to select the cosmic rays for each frame. And then by combining many different frames, we can produce a final image. And the overall accuracy about 97%. And there are some false positives, for example, in some bright stars, some cosmic rays cannot be recognized. So we have analyzed all these and put it into our photometric pipeline, and it seems that our science goals can be achieved by this sort of algorithm. Now, we are also doing CMOS detector experiments, and this shows the detector inside here, and this is a cryogenic system. So one worry is that after 4 years, the cosmic rays will cause a very dramatic increase in dark current, maybe 50 to 100 times higher, and also the quantum efficiency will decrease. So we have currently 2 candidate CMOS detectors, one in optical, the other one is more red sensitive, and the experiment being done actually this month in China. Hopefully we will select the right CMOS detector in April this year. So this is the current ET timeline. So the detector selection, as I mentioned, will be April this year, and the prototype will be constructed starting from June this year, and telescope and satellite construction will be in December next year, and the launch will be in October 2028, and the first microlensing season will start in March 2029. Now, many people ask me about data policy. This is still being discussed. My personal preference, and indeed the microlens team's preference, is to publicly release all the data within 48 hours, just like Roman, and share with the worldwide community. So the total data rate is not tremendously high, but still quite high, 64 terabytes for 4 years. And with intermediate product, this may reach a factor 5 to 10 high. So we hope to release new microlensing events and data points, also models and data we take from KMT-net and other telescope time we can obtain in the future. So you can see, we hope to be as open as possible. So in the current age of geopolitics, of course, international collaboration is not easy, but we are completely open to international collaborations. Indeed, they are very welcome for a variety of purposes, not only for science. So you have some ideas, we'll be very happy to discuss with you. Now, of course, with this sort of data, we are manpower challenged. So I'm moving to Westlake University to establish a new department of astronomy with 20 faculty members. So this university is very new. So it started in October 2018. And this is in the beautiful city of Hangzhou. There is a Chinese proverb which says paradise in heaven and Hangzhou on earth. So you can see it's a beautiful city with thousands of poems written in Chinese history. So it's a private and public funded university folks, which has only basic science. So now it has more than 200 faculty members. So astronomy, you can see, occupy a substantial fraction from 15 different countries, I should emphasize. So international faculties are welcome with more than 2,000 graduate students and more than 400 postdocs. So as advertised before, I should say we also have 2 postdoc positions available. So to work on Earth 2 and also data from other facilities. So if you are interested in working in Asia, you are very welcome to join us in this beautiful campus and I think extremely ambitious new university in China. Now, let me finish my talk with a summary here. So I hope I have conveyed that there are multiple ways we can achieve a mass function with microlensing planets with a number over 100 from ground, from space, with various space satellites. And also with Earth 2 satellite, although the aperture is smaller, I hope we can still achieve very significant science, including measuring the masses for more than 300 found, in particular, free floating planets and white dwarf planets in the future. So I want to emphasize that ET is really complementary to Roman, and collaborations are very welcome. Okay, I will stop my talk here. Thank you.
Exciting to talk about the 2 questions. So, if you're doing thermal thickness observations with Roman, the sensitivity will probably depend on actually the parameters of the two L2 halo orbits.
Right.
So do you think you have an option to try and adjust those parameters to make them optimal for, free floating planet masses, at the times when you could have simultaneous observations with Rome?
I don't know whether it's possible. The science driver, the primary science driver in the past was for transit. So we just tapped the main mission. So I'm not so sure whether it can be adjusted. But even in the same halo orbits, it will be at different phases, right? So it's still possible to do parallel in that way. But that's a good question. I will ask the satellite people to see whether it's possible.
So just to say, we looked into this for Euclid, and my understanding is it's next to impossible because it's really going to depend on the delta V's of the rocket. There's no way they can necessarily tune the orbit insertion to that level.
But the phases will be different, so the separations may still be interesting.
Well, I mean, it's still.
Right? Sorry?
Presumably the orbital phases of two missions are not too relative to one another. Yeah, unless you have a way of not making that happen.
Any other questions?
Actually, one of the main problems you will face with the branding, because with the 35 centimeter telescopes, you will have a lot of confusion between source and the surrounding stars. So, are the simulation taking into account branding?
Yes, I think Hongjin takes into account the PSF will be similar to. He will talk much more about this. So he took into account many of these effects, even the effect of vibration on the PSF and various effects.
So I have a question about, you mentioned DECAM and other ground-based facilities in the coordination of providing complementary observations. And I'm 100% behind international collaborations in this respect. I'm aware that certainly for the improvement community, there's a lot of effort being put out towards coordinating large proposals across the community to some of these survey-style 4-meter class follow-up facilities, precisely because there aren't enough of them. And in order for any one group to get enough time, you really have to coordinate with a lot of communities. So those efforts are underway now in the Rubin community, and I really encourage everybody, but yourself especially, to get involved in that conversation and support those proposals, so that we can get DECAM time and CFHT time and all of the rest, and get it pointed at the Roman field especially, and within the S2 field pointing.
That's a very good point. So I think Wilson, as a PI, already got some time on DECAM. So he's interested in doing very frequent observations to test very, very low mass planets using DECAM data, and Matthew Penny also has some data on that. So in the future, it will be useful to coordinate. For CFHT, it may be easier. We can buy the time to do it. And I think my new institute, we can possibly do that. So yeah, I think maybe we should talk about this. Yeah.
I'd like to.
Yeah, thank you.
Any questions?
So I was surprised you only get down to 20.5, given a 35% of your aperture. If you scale off the tests, you should be able to get deeper. Do you understand where your throughput limitation is coming from? Is that on the detector or?
I think Hongjin hopefully will answer this question. He has done all the simulations. Yeah.
Okay, last call for questions, and anybody on Zoom as well, just if you put in the chat you want to ask a question, it should pop up on our screen on those. Okay, otherwise, yeah.
I want to talk about the field selection that you mentioned that you're doing the light curve simulation and CMC. I guess what were you optimizing for? Event rate or biggest separation between like spacing ground or something else?
They think our goal is to achieve the highest event rate, to have the highest number of free floating Earths. Because this is Earth 2 mission, so we have to find some free floating Earths. And that is what's being optimized here. In order to convince the funding agency, we can put microlensing into the same mission as transits. But fortunately, we can do this in the same mission.